Artificial intelligence is a moving target. Unlike legacy software, modern models ingest new data and adjust their own internal parameters, creating capabilities that outpace traditional static validation tools. This creates a gap in organizational oversight. Many companies define values like equity or fairness in policy documents, while lacking the reporting lines and audit trails needed to enforce those values in production. This image of a glowing neural circuit represents the black box of machine intelligence. To address the risks of opaque decision-making, the Association of Southeast Asian Nations developed the ASEAN Guide on AI Governance and Ethics, establishing a regional standard for interoperability. The framework identifies 7 guiding principles: transparency, fairness. These principles are integrated directly into the AI system lifecycle, beginning at the problem definition stage and continuing through post-deployment monitoring. This integration is a response to the current development landscape. While the proliferation of open-source technology has lowered the barrier to entry for AI, it has also increased the need for centralized corporate accountability. Responsible AI is an engineering requirement, built into the development pipeline from the first line of code. Trust in autonomous systems is the result of specific architectural choices made during the design phase. Implementing these choices starts with internal governance. Because AI projects carry different levels of risk, organizations use tiered reporting structures to manage oversight efficiently. This diagram from the GSMA playbook shows a 3-tier escalation model. At level 1, responsible AI teams handle routine self-assessments. Complex cases move to level 2, reviewed by an ethics committee. Highest risk cases reach level 3, where the executive board makes final deployment decisions. Singapore's Smart Nation Group uses a similar gating mechanism for teams developing custom applications with an LLM. An LLM, or large language model, is an AI trained on vast text datasets to generate human-like responses. To prevent unsafe deployments, product teams must secure approval from a central AI workgroup before they begin beta testing with outside users, and again before a full rollout. These escalation paths and approval gates provide the organizational architecture necessary to enforce accountability. Beyond organizational oversight, developers must determine the exact level of autonomy granted to each AI agent. This graph maps the required level of human intervention by plotting the probability of a negative outcome against the severity of that potential harm. The bottom left quadrant represents minimal risk. Systems in this zone use a human out-of-the-loop architecture, allowing for autonomous execution. Gojek utilizes this architecture for its automated promotion allocation, which distributes discounts to users based on behavioral profiles without requiring human screening. The medium risk zone triggers a human over-the-loop architecture. In autonomous vehicles, the AI drives the car, but a human supervisor remains present to monitor the system and take manual control if needed. The high-risk quadrant mandates a human in-the-loop architecture. In healthcare diagnostics, an AI might analyze a scan to predict a condition, but a human doctor must evaluate that recommendation and execute the treatment plan. This architecture requires operators to stay alert for automation bias. This occurs when humans become accustomed to a system's accuracy and begin reflexively approving outputs, potentially missing occasional errors.
Organizations determine a system's position on this graph by evaluating harm within the context of their specific industry and the diverse cultural norms of the ASEAN region. The level of human intervention is a direct response to the system's risk profile. As the probability and severity of harm increase, the architecture moves from autonomy toward direct oversight. This risk profile informs the entire AI operations lifecycle. This lifecycle consists of 5 stages: problem definition, data collection, modeling, outcome analysis, and deployment. In the data collection phase, engineers must ensure datasets represent the target population. Data lineage tracks a data point's path from raw intake to model injection, creating an auditable trail. This prevents reinforcement bias, where a continuous learning model ingests its own biased outputs as new training data. Ucare.ai used specific data collection methods to mitigate proxy bias in its healthcare cost prediction models. Instead of using generalized third-party datasets that may contain demographic biases, they built models using localized data from client hospitals, tailoring the system to specific patient profiles. Maintaining data provenance is the only way to ensure a neural network is built on a solid, reliable foundation.
After processing the data, the pipeline moves into modeling and outcome analysis. Developers balance model explainability with robustness. In complex black box algorithms, it is often difficult to interpret the exact weighting of variables used to reach a decision. If a model cannot be directly explained, teams use auditability as a substitute. They maintain a centralized process log that documents all design decisions and hyperparameter settings used during development. These details are summarized in an AI model card, a technical document that discloses the model's performance metrics, testing environments, and limitations to deployers. Once the model is documented, it undergoes outcome analysis. Engineers use adversarial testing to observe how the system handles unexpected inputs before entering a live environment. Gojek conducts this analysis by testing models against predefined offline benchmarks. By running iterations against a fixed set of historical data, Gojek can isolate and measure performance changes without exposing end users to real-world risk. Rigorous offline testing and detailed auditability create a transparent development process, even when the underlying algorithm is complex. Following deployment, the AI system operates in a highly dynamic live environment, constantly processing unpredictable real-world inputs and interacting with human users. This chart illustrates data drift, which occurs when real-world input data begins to diverge from the original parameters used during training. If drift causes performance to drop below a specific threshold, the system triggers a review by the ethics committee, restarting the design escalation process. This connectivity makes stakeholder communication an essential part of the system's technical operations. Organizations disclose AI usage to users and provide review channels where individuals can request human intervention for automated decisions that affect them. User feedback functions as an additional sensor. The data from these interactions flows back into the problem definition and data collection stages of the next development cycle. The ASEAN Guide treats ethical AI as an operational cycle. Responsible AI relies on continuous risk calculation, structural oversight, and technical adaptation to manage these systems in the real world.